We are going to derive formula for kinetic energy. Kinetic energy is energy of an object due to its motion. The scenario here is that we have got an ice puck on ice. It is at rest, so Vi equal to 0. We apply a constant force as shown here, and as a result the ice puck gains speed, and after some time the speed of ice puck is Vf. During this process the displacement of the puck is delta x. We are ignoring the friction between the surface and the object. So constant force is applied on the puck. It means that it is undergoing constant acceleration and the puck speeds up and it gains kinetic energy. This must be a puck here, not box. Work equals to change in energy. What is the reason for writing this equation? It is work energy theorem. Now I can write delta E as delta KE. Why so? Because here the only change in energy is kinetic energy. The puck is not gaining any height and there is no elastic potential energy present here also. So only change in energy here is kinetic. And in this next step we have just expanded delta. So change in kinetic energy is kinetic energy final minus kinetic energy initial. And this is equal to the work done. I'm going to label this equation 1 because we will need it later on. Now we can also write work done by this formula. Work done equals Fd times cosine of theta. Why can we write this equation? Because this is definition of work. In the situation here we saw in the previous diagram that the force was to the right horizontally and displacement was also to the right. So the angle between the force and displacement was 0 degrees. So I'm going to substitute 0 in here. So cosine of 0. D, the displacement, was labeled as delta x in the diagram. And why can we replace F by ma? Because F is the only force that is acting. So F net would be equal to F, and we apply Newton's second law. We simplify it further, so we are left with ma delta x. We are going to label this equation 2. We will come back to it later on. Because the force is constant, it means that the acceleration is constant, and we can apply the kinematics equations of constant acceleration. So one of the equations, kinematic equations that does not use time, is this one. Vf square equals Vi square plus 2a delta x. We rearrange it, take Vi square to the other side and divide by 2a. We get this expression for displacement. Now we can substitute this formula for displacement in the equation 2 here. When we substitute it, ma delta x, instead of delta x we put this expression. Now how can we simplify this? First of all, we can cancel out a's, and then I can distribute mvf square minus mvi square, and it can also be simplified as half mvf square minus half mvi square. So let us label it as equation 3. Now let us compare equation 1 and equation 3. Equation 1 was this one. Work done equals to the final kinetic energy minus the initial kinetic energy, and work done equals half mvf square minus half mvi square. Because the left hand side of both these equations are same, it means we can compare these two. And we started with initial velocity of 0. The puck was at rest, so kinetic energy was also 0. If we compare, then we can say that kinetic energy has formula of half mv square. So we have derived the equation for kinetic energy. Kinetic energy has units of energy which are joules, which means that we should get joules from the right hand side of this equation also. Half does not have any units, so if we simplify the units of mass and velocity square, we must get joules, and this can be shown like that. Mass has units of kilogram, velocity has units of meter per second, and we square it, then we simplify it. Now we can write m square as m multiplied by m. So we see that kilogram meter per second square is equal to newtons. So newtons times meters, which is equal to joules.